So I'm going to get ahead and get started on Chapter 19, the respiratory system. Introduction. What does the respiratory system do? It filters the air, transports it into the lungs, into the microscopic air sacs where gas exchange occurs. Microscopic air sacs are referring to the alveoli. So you can kind of think of the alveoli as the functional unit of the kidney. And when we're talking about gases exchanged, we're talking about primarily oxygen and carbon dioxide. So again, respiration is the process of exchanging gases between the atmosphere and body cells. And it consists of the following events. That's breathing. And a lot of times we think of breathing as respiration, but breathing is also called ventilation and inhalation and exhalation. Respiration, for the purposes of this lecture, will be more referring to gas exchange. There are two types of respiration, or two primary places where respiration or gas exchange occurs. The first one is external or pulmonary respiration. That occurs in the alveoli, again, which is part of the lung and the blood. So what's external about this is where the gases come from. And we're going to talk about what happens to oxygen, in which the pulmonary capillaries gain oxygen and lose CO2. There's also the transport of gases. Hemoglobin is the primary transport for oxygen, where bicarbonate ions are the primary transport system of CO2 in the blood. Then we have internal respiration. And again, this is the exchange of gases between the systemic capillaries. So this is occurring throughout the body. And the blood loses O2 and gains CO2, or loses oxygen and gains carbon dioxide. Another type of respiration that occurs is cellular respiration. And this we reviewed way back in Chapter 3. But notice oxygen plus sugar, this happens to be glucose, yields ATP. ATP is the source of cellular energy, yields water, and CO2. So CO2 is a waste product, hence why we breathe out CO2. Oxygen, on the other hand, is needed in order to create ATP. So when you think about what you're breathing in and breathing out, you want to breathe in fresh oxygen, and you want to breathe out the waste, CO2. Okay, wrong button. There we go. This slide is pretty much a rehash of what I've just said, but there's one important part, and that's this equation down here. Okay, this is carbon dioxide and water. It will yield here, this is carbonic acid plus hydrogen ions, and this is bicarbonate. Now, again, I've said that bicarbonate is how CO2 is transported in the blood. But notice we're talking about acids, which carbonic acid is, and we're also talking about bases. So another function of the respiratory system is to help maintain the internal pH of the environment. And that's done via this equation right here. And we'll talk more about this equation momentarily. Now, the organs of the respiratory system can be divided into two tracts, upper respiratory tract, so nose, the nasal cavity, the sinus and pharynx, allergies I always think of when I think of upper respiratory tract. You can get upper respiratory tract infections. Lower respiratory tracts include the larynx. The larynx is right here, if we're looking at the figure on the right, this is where the vocal cords are, and it is the opening to the trachea, which is right here. We have the bronchi, and they branch, so you get the bronchial tree, and they're carrying the air into the lungs, which of course are right here. So if you have a lower respiratory tract infection, that's an infection in this general area here. Functionally, you have two zones. You have the conducting zones, and the conducting zones means it's just carrying air. So all the way from the nasal cavity all the way down into the bronchioles. Now the respiratory zone is a bit more microscopic, and the respiratory zone is the site of gas exchange. So this is going to occur primarily in the alveoli, and the alveoli is the key word here. So this is the smallest order of branching, and respiratory zone is where carbon dioxide and oxygen are going to be exchanged. Okay, so now we're going to talk about the mechanism of breathing. So if you breathe, you notice why your thoracic cavity, your lungs expand, and then when you exhale, you notice they contract. So we're going to talk about why that is here. But first we're going to talk about Boyle's law. And one way to visualize Boyle's law is using a syringe. So basically what Boyle's law says is that pressure is inversely proportional to volume. So the larger the container here, the lower the volume. The smaller the container, the higher the pressure. Okay? So again, big volume, low pressure, small volume, higher pressure. And because of this, Boyle's law, this is why air moves in and out of the lung, due to Boyle's law. All right, let me erase these. So what we're trying to overcome or become less than is atmospheric pressure. And atmospheric pressure at sea level is 760 milligrams or millimeters of mercury, which is what this stands for. And when you inhale, your lungs expand, and that increases lung value. So that decreases in the lung area, that decreases the pressure. Okay? And what it decreases the pressure to is, if I could get my highlighter here, 758. And that is just slow enough to cause the air to come into the lung. Okay? So the main muscle responsible for inspiration is the diaphragm. And that is innervated by the phrenic nerve here. You might have heard the rhyme, C3, 4, and 5. That's in reference to the phrenic nerve. Keep the diaphragm alive. Okay, let's talk a little bit more about this. So what happens in inhalation? Whoops, let me get this erased. What happens in inhalation? And inhalation is referred to as active because of muscle contraction. And the most important muscle is the diaphragm. So when it contracts, it lowers, and it is responsible for about 75% of the air coming in during normal breathing. And in normal breathing, each normal breath at rest, you take in about 5 milliliters of air. That's roughly, well, one can of Coke is like 320 mils, so a little bit bigger than a can of Coke. That's the amount of air you take in. And then you can take in 4 to 6 times that when you exercise. The other muscles important for inhalation are the external intercostals. Intercostals are the muscles between the ribs. They're just one set. They're the external or the outer. And they're responsible for about 25% of the air entering. Now, should you begin to exercise, these muscles come into play: sternocleidomastoid, the scalenes, and the pectoralis minor. These are going to help elevate the rib cage even more to bring in more volume. And again, more volume equals lower pressure. So again, when the thorax expands, you have to overcome something called surface tension. Remember, your lungs are covered in pleura, serous pleura, so parietal and visceral pleura. These are the serous membranes that cover the lungs. And so they have to overcome that. And they have to overcome surface tension. And surface tension is the attraction of polar water molecules. In other words, it wants to keep liquids as close together as possible. So that's what surface tension wants to do. So you need to overcome surface tension in order to increase the volume. So when you inhale, you overcome the size and you overcome surface tension, and that causes a decrease in interpleural pressure. And remember, pleura is a suffix for lung. Okay, so when you decrease the pressure in the lungs, air again comes rushing in. Expiration is basically from the relaxation of the diaphragm. So expiration is thought of as passive. Also, it's from the elastic recoil of the lung, and that's kind of what it says it is. Elastic recoil, remember, the lungs have also stretched. So like a rubber band, after you stretch it, it wants to go back to its original size, which was smaller. And also, surface tension takes over and makes the alveoli in the lung also very small, or as small as possible. And when all this contraction and recoil and surface tension occur, you make a smaller volume. Therefore, you increase the air pressure about 1 milligram of mercury above atmospheric. So when you expire, air comes out and re-enters the atmosphere. Again, the purpose of expiration is to make the pressure in the lungs greater than atmospheric pressure. It is normally passive. It's based on recoil of the elastic fibers, surface tension in the alveolar fluid. Remember, the lungs are covered in fluid, not a lot, but just enough. The diaphragm relaxes. The external intercostals relax. And again, as these two muscles relax, you increase pressure, air pressure in the lungs, and that causes expiration. Now, if you're exercising heavily and you're doing forceful breathing, then you incorporate your abdominal muscles and another set of muscles between the ribs called the internal intercostals. Now, airflow. What drives the flow of air? Well, the primary factor is air pressure differences. things are moving, you can kind of think of diffusion. Things are moving from higher pressure to lower pressure. 3 other factors affect airflow. Surface tension, which we've already talked about. Again, surface tension is the attraction of water molecules. And again, the lungs aren't floating in fluid, but there's fluid there. Again, the serous membranes and other fluids. And what they want to do is make the alveoli as small as possible. Now, you don't want the alveoli too small, because if it's too small, it will collapse. So you need to overcome surface tension. Your body makes a molecule called surfactant, and that helps overcome or reduce surface tension, so you can, one, your alveoli don't collapse, but also, well, that's the primary reason, so your alveoli don't collapse. Surfactant is also given during acute respiratory disorder in premature infants. Surface tension also accounts for 2/3 of the lung elastic recoil. Okay. Another aspect of airflow is lung compliance, and this is the fibers in the tissue. So it's the elastic fibers in lung tissue that are activated. In other words, the more stretchy the lung fibers, the easier airflow is. So things like scar tissue and too much fluid causes the lung to lose the elasticity and therefore makes it harder to breathe. The other component of airflow is airway resistance or airway diameter. A larger diameter has less resistance. One way to think about this is if you think about drinking a milkshake. If you use a big straw, it's much easier to bring the milkshake in than if you're using a coffee stirrer, let's say. So our bodies can regulate the lumen of the, particularly the bronchioles, because they are covered with smooth muscle. So the autonomic nervous system can regulate the size of the bronchioles, just regulate the amount of air that comes into the lungs. And that's all I want to say about this slide. Okay, normal breathing is rhythmic, involuntary. In other words, you don't usually have to think about breathing. Although, now that I've said something about breathing, you're probably thinking about it. So you can control your breathing. So when you take yoga, you can take your deep breaths in and exercise. But you don't have to. The 2 main areas of the brain responsible for breathing are found in the pons. This is the primary one, respiratory group in the pons. The other is found in the mighty medulla oblongata. Okay, these are both located in the brainstem, and these are the 2 areas that regulate breathing. There's other things or other factors that regulate breathing as well. One is the partial pressure of oxygen, which is PO2. Again, we're talking about partial pressure because the air we breathe is a mixture of nitrogen, oxygen, carbon dioxide, and other gases. So part of what we breathe in is oxygen, about 21%, 22%. The partial pressures of carbon dioxide, or PCO2. How much stretch is in the lung. Also your emotional state, crying, yawning, lots of things, laughing. These are also activities associated with the respiratory system. And of course your level of physical activity. Now all this is measured by a couple different types of receptors. You have mechanoreceptors. These guys are going to be measuring stretch of the lung. Whereas the chemoreceptors down here, these are going to be monitoring chemicals like your oxygen and carbon dioxide levels, and also it's going to be measuring your pH. Remember, carbon dioxide and pH are closely related. Now let's talk about how gas exchange occurs. And molecules, as you know, you'll see diffusion here. When molecules diffuse, they go from an area of higher concentration toward a lower concentration. Okay. However, in respiration, we're thinking partial pressures. So gases are going to diffuse from areas of higher partial pressure to areas of lower partial pressure. And to do that, the respiratory membrane has a couple of unique features. It is very thin, and it also helps gas exchange occur rapidly. So let's talk about some of the features. Okay, and let me erase. Oh, no. Okay. So let's talk about the respiratory membrane. First we have the alveolar wall. Remember, the alveolar wall is, the alveoli is alveoli is plural, alveolus is singular, and it's talking about the area in the lung where gas exchange occurs. You'll find a couple different types of cells. The main ones we're going to talk about are type 1, and it's simple squamous epithelium, one cell layer thick. There's also the type 2 cells found in the alveoli, and these are going to secrete surfactant. And remember, that's going to help you overcome surface tension. There's a basement membrane for the epithelium, because again, all epithelium rests on a basement membrane. Then you have a capillary basement membrane. And the reason why you have that is because the capillary itself is made of simple squamous epithelium. And here is your capillary right here. So, basically, the gases have to pass through 2 layers of simple squamous. And altogether, that's only about 0.5 microns thick. And that's a micron is a millionth of a meter, so less than that. Now, because it's so thin, that's going to allow gases to diffuse more rapidly and more efficiently. And here's a picture. I think it's a really cool picture. That's my job. Okay, so here you have the alveolus here. Here's the capillary. And remember, capillaries are so small that only one red blood cell at a time can go through. So they go through single file. And it's between this here, this very thin membrane, 2 membranes actually, that gas exchange occurs. Remember, there are 2 types of respiration. Well, 3 if you count cellular. But the 2 main types of respiration we're going to talk about is external respiration, and that occurs in the lung, in the alveoli. And in external respiration, the external is referring to the fact that oxygen is coming from an outside source. And oxygen is going to diffuse from the alveoli, where the air pressure is high, into the capillary, where the pressure is lower. Okay, and again, a diffusion will occur till you reach some type of equilibrium. Carbon dioxide, on the other hand, is going to diffuse from the blood, deoxygenated blood, into the alveoli, which is lower. So again, it's going to go from where the pressure is 45 to where the pressure is 40. And again, this will continue until you reach some type of equilibrium. So here we are. Again, this is the alveolus. Let's see, use the spotlight here. This is the alveolus. Okay, here's the capillary. Okay, remember this is deoxygenated blood, so it has a whole bunch of carbon dioxide, so it has a higher pressure of carbon dioxide, so carbon dioxide will diffuse out of the capillary into the alveolus. The alveolus has taken in, you've just breathed in, so the pressure, partial pressure of oxygen is very high, so the oxygen is going to diffuse from the alveolus into the capillaries. Internal respiration occurs in all tissues throughout the body. So oxygen, now we have oxygenated blood, so the systemic capillaries have a higher pressure than the tissues. So oxygen is going to flow from the capillaries into the tissues, again until you reach some type of equilibrium. Carbon dioxide is going to flow from the tissues. Remember, the tissues are making carbon dioxide as a waste product of cellular respiration. So in the tissues you have a high level of carbon dioxide, and it is going to flow into the systemic capillaries, which has a lower partial pressure of carbon dioxide until we reach equilibrium. Now when you're at rest, say you're binge watching Breaking Bad, you only use about 25% of the available oxygen. So when you're at rest, deoxygenated blood has about 75% of its oxygen capacity. This is good because when you decide to go to the fridge, or like me, if you decide to get some Cheetos from the kitchen, you need that oxygen to help power your movement. So you have oxygen available. All right, so let me tie in a couple of, let me erase all drawings here. And we'll go back to the spotlight. Here is internal, here is external respiration. Okay, now you have pulmonary capillaries. So external respiration occurs in the pulmonary circuit. The pulmonary circuit refers blood flow from the heart to the lung and from the lung back to the heart. Okay. In external respiration, oxygen will enter the blood and carbon dioxide leaves the blood. Okay. Once we exit the heart through the aorta, now we're going into systemic circulation. And in systemic circulation, you have internal respiration. So oxygen will leave the blood, so the blood becomes deoxygenated, and carbon dioxide will enter. And of course, through the vena cavas, the blood will re-enter the heart and will start the pulmonary circuit again. Now the rate of pulmonary gas exchange again depends on partial pressures. So again, we're going from higher to lower pressures. The surface area. The more surface area, the easier gas exchange is. So if you unfolded the lung, again, the alveoli are nice and round. They look like little grapes. You get 75 square feet of lung tissue. Diffusion distance, remember this was only 0.5 microns. Also molecular weight and solubility. Okay, so we know that blood and carbon dioxide can leave and enter the blood. Now we're going to talk about what molecules are responsible for the transport of these gases in the blood. Let's talk about oxygen first because that's the easiest. Hemoglobin. Okay, hemoglobin is the molecule that's going to carry almost all the oxygen. Now you might see here that the bond between oxygen and hemoglobin is unstable. And you might think, well, that's not very good. But actually, in reality, it's quite good. Because the bond is unstable, that means hemoglobin can release the oxygen. For example, carbon monoxide, CO, also binds to hemoglobin, but the bond is very stable. So your hemoglobin really doesn't want to let go of carbon monoxide, and that causes lots of problems. Again, about 75% of the oxygen remains bound to hemoglobin at rest. That ensures safe CO2 levels and also helps keep regulating your pH. What this drawing is showing you, again, we have our friend the alveoli, or alveolus. In red are the oxygen molecules. And in external respiration, oxygen goes into the bloodstream and it binds to hemoglobin molecules in the red blood cell. It's transported to the body, and in internal respiration, the hemoglobin will let go of the oxygen so it can diffuse into the cells and power cellular respiration. All right, what do we have here? Well, we have something called a dissociation curve. On this axis, we have saturation of hemoglobin. So that means the amount of oxygen bound to hemoglobin. And here we have the partial pressures of hemoglobin, partial pressure of oxygen. So, here is our magic number, 75%. This number is important because 75% is when blood is normally deoxygenated. Now, as you increase that partial pressure of oxygen, you'll notice you'll get to 100% saturation, and the hemoglobin cannot bind any more oxygen. Now, factors that regulate the release of oxygen from hemoglobin, there are three. The first one is pH, and we're going to start with this middle line here. This is normal pH. Now, if the pH starts to drop and the blood becomes more acidic, what this is saying, higher acidity means more carbon dioxide. So this curve shifts to the right, and what that means is that hemoglobin is going to let go of oxygen more easily. When the pH, in this line to the left, when the pH is higher, more basic, then hemoglobin is going to hold on to the oxygen more. Okay. So it's no coincidence that pH and the partial pressure of carbon dioxide, their saturation curves look quite similar. So here in the middle is 40 millimeters per mercury of carbon dioxide, normal carbon dioxide levels. Now when we increase carbon dioxide levels to 80 millimeters per mercury, which is in the brown here, what this is saying is that hemoglobin will release oxygen much more rapidly, or much more easily. Now, should our levels of carbon dioxide go down, our partial pressure of carbon dioxide go down, what this is showing you is that hemoglobin will hold on to oxygen more tightly. The other factor that affects how hemoglobin releases oxygen is temperature. 38 degrees Celsius, this is normal body temperature here. Now, when body temperature goes up, that could be a sign that we are, let's say, exercising. So hemoglobin is going to let go of oxygen much more easily when our body temperature goes up. Now, as our body temperature cools, hemoglobin is going to hold on to the oxygen much more tightly. Okay, this leaves us just carbon dioxide transport. Carbon dioxide is transported in the blood 3 different ways. It can be dissolved right into the plasma, and that's about 7%. 23% binds with hemoglobin. And what it's binding with, hemoglobin has a heme component, which is the iron, and that's going to bind to the oxygen. The globin is the amino acids, and that's what's going to bind the carbon dioxide. However, the majority of carbon dioxide is carried as a bicarbonate ion, so that's 70%. Now the enzyme, which is found in red blood cells, carbonic anhydrase, takes carbon dioxide in water, converts it to carbonic acid, and which dissociates, means breaks the parts, and forms hydrogen ions and our friend bicarbonate ion. So this is the equation we've seen earlier in the lecture. Okay, so what's this illustration showing? So here's the cell. Remember, the cell is releasing CO2. It's producing CO2 as part of cellular respiration. So the CO2 is going to leave the cell. Part of it is going to be dissolved directly into the plasma, the liquid portion of blood. 23% is going to combine with the globin, the protein part of hemoglobin, whereas 70% is going to, again, enter the blood cell, be converted into carbonic acid, which dissociates into the bicarbonate ion. And this bicarbonate ion is going to leave the red blood cell and go into the plasma. So this brings us to the chloride shift, or chloride ion shift. So what happens is that the bicarbonate ion diffuses into the plasma. So as that occurs, you get a loss of negative ions. So to replace the loss of negative ions, you get chloride, which is also negatively charged, move into the red blood cells from the plasma. So when bicarbonate ion, so I'm down here at the picture, this is the red blood cell here. When bicarbonate ion leaves the red blood cell and goes into the plasma, chloride ions are moved in to the red blood cell, and that's going to keep your negative charges balanced. And conversely, when bicarbonate ion moves back into the red blood cell, which it has to do in external respiration, then chloride ion will leave. So they kind of go in opposite directions. What this is showing you, again, here is external respiration. Here's the alveolus. Here's the capillary here. That 7% of carbon dioxide diffuses out. The hemoglobin, or the globin part, lets go of the carbon dioxide. And then the bicarbonate ion returns to the red blood cell. So chloride ions leave. And it is converted back to CO2 and water, and the CO2 diffuses out. And my last slide shows, this is table 19.7. You're going to find this in your book or on your website. And this is just a very lovely table talking about the way oxygen and carbon dioxide are exchanged. And that is the end of my lecture. So normally I'd ask if there's any questions. So if there are, please let me know. And thank you very much.